Hey guys, how's it going? Our House 21 again with another installment of my RC Physics series. Now, this time I want to talk to you about something a little bit different, and I'll try not to make it too complicated, but it's something that a lot of guys have touched on, but don't really seem to go all the way in. So I'm an all-in kind of guy, so here we go. So this time I want to talk a little bit about the relationship between power and force and what it means for the speed of your RC. Now you see here I've got my Rustler collection. Actually, it's not all mine. This is my son's Rustler, which is in full basher configuration right now with some big old Proline Thrasher tires or Trencher tires going on. Then I've got my guy here, which is set up in speed configuration. And I've mentioned in previous videos that I've got quite an assortment of tires, so I can configure these guys out pretty quickly and other for whatever applications wants to suit our needs of the day. And then right here I've got this VXL, which I'm actually building up from scratch. He is intended to go on eBay. So this is built around a Castle Creations Sidewinder SV3 setup. You can see here with my trademark high power cooling fan on top with a Castle 1406 motor going through 5700 kV. So this guy is going to be a pretty speedy little guy, and he'll be gracing the pages of eBay here very shortly. So feel free to dive in there and take your shot at him. But anyway, back to the lesson at hand. So a lot of guys are trying to get a lot of speed out of these cars, and and they are obviously capable of doing it. You've seen the guys going over 114 miles an hour. That's Draven, and Geo Stealth, and all the other guys who are out there in the 100-mile-an-hour Wrestler Club, mostly accomplishing that goal by putting very large, eighth scale, 2200 or so kV motors, running 6S LiPo with the Mamba Monster speed controllers and all that. And yes, they've accomplished the goal. They kick some serious tail. But the problem with these setups is the fact that in order to get that extra power, you have to add a lot of extra weight. So just looking at my little scale here, you see this is my Venom 5400 milliamp hour 20C 3S LiPo pack. So scale zero out, throw it on there. It comes in at 14 ounces. So this guy is just short of a pound. You throw two of these guys onto a vehicle, so now you're carrying an extra pound of weight. The dry weight of one of these Rustlers, is only about 4.5 pounds. So now to go for 6S LiPo, you're carrying an extra pound. In order to make the weight balance, because these Rustlers are notoriously tail heavy, then you need to add another, well, now you're carrying, like I said, two battery packs, which have to be weighed in here, whether you're stacking whatever. Then you need to add additional front weight to counteract the CG difference. So now, the guys are adding between a pound, pound and a half, of weight up right over the front axle. So now you go from a, what could have been a 5-pound RC to something that's getting closer to 6 or 7 pounds. So why is mass so important when building a fast RC? Well, the easiest way to jump into this is to do something that might scare some of you guys. Just jump right into the math. So I took a few minutes and put together, just some simple equations to try to illustrate some of the relationships between the factors that are going on here, just to make it a little bit easier for people to follow. So let's start off, where engineers tend to like to start off with the good work of Sir Isaac Newton. So F equals ma. Any discussion about force versus power needs to start off at the first principles, and this is the first principle. So if you look here, what this is telling us is that for a given force, well, the force acting on the object equal to the mass times its acceleration. Okay? So, but what you can also do by rearranging this equation is calculate what the acceleration an object will feel is based upon the amount of force that you put on it and the amount of mass that the object has. So like you're saying, in the case of our RC vehicles here, this wrestler here is about 5.5 pounds. The Success Lipo guys, by my estimation, should probably be somewhere between 7 and 8 pounds. Okay, so why that becomes important is it starts to limit the amount, or actually it sets the amount of power that one of these vehicles can push to the ground. Let me explain. So, by definition, the amount of force that you can put onto a wheel is equal to the friction force that you're feeling at your wheel. And that force is equal to the weight of the vehicle times the coefficient of friction of your tires. So, in this situation, I'll just use my diagram here. So, you have the weight of the vehicle pushing down, and you have your coefficient of friction, which is basically the amount of stiction between the wheel and the surface that you're on. And for average objects that could be like 0.3, but for rubber, it's which is why we use it for tires, it can actually be anywhere between 1 to 2. So to make the math easy, I'm just going to go ahead and assume a coefficient of friction of 1. Okay, so if you use a simple equation, if you have an 8-pound vehicle, which is what you see right here for your Mama Monster or Success setup, if you have an 8-pound vehicle, your friction force that you can feel, the maximum friction force that it can push, will be about 8 pounds. So you think, okay, well, here, just thinking ahead to my next line, well, that obviously says that, for my 1410 setup, I'm inherently inferior because here my vehicle only weighs about 6 pounds, so my maximum force I can push down is only around 6 pounds as well. Well, that would be true if it wasn't not true. So basically, that is correct. However, once you take into account the mass of the vehicles, remember the equation: acceleration equals F over M. And since in this situation, the uh, Mama Monster 6S setups are about 25% heavier, but the force is about 25% greater, that you're putting down to the wheels, but my 1410 setup is 25% lighter. So the two items cancel each other out. So basically, for both situations, you end up with the exact same maximum acceleration, which in this case, by my simple numbers, is approximately 1g of acceleration. That's good stuff, because if you just plug in simple physics, you know, if you can have 1g of acceleration, that will give you a 0 to 60 time of less than 2.7 seconds. And remember, I said that this force is actually can vary between 1 to 2. So based upon a tire compound that you have here, this could be as high as 16 pounds of force, which will make your acceleration, twice as fast. So potentially, with the right set of tires, you could get 0 to 60 times. I mean, this is already in supercar territory, but we're talking about insanely quick acceleration. But again, why is so if everything cancels out, what's the big difference? Well, the lighter that you can make these vehicles, the more weight you can take out, the better that acceleration is going to be. And oftentimes it's easier to take a little bit of weight out of a vehicle than it is to try to get additional force. That means that if you can make your vehicle smaller, lighter, you can get by with a less powerful motor and get similar performance. And the racers have been on that for eons. But that's not the whole story. So let's go on and talk about how that relates to your overall top speed. Well, if you look at the equation down here, when you're at maximum speed, or actually when you're at any speed where you're no longer accelerating, so in the highway, cruising down the road, the force that's pushing on your wheels, so your wheel force, is equal to the aero drag of your vehicle. Now, there's some other things in here. There's mechanical drags and that sort of things, but I'm gonna kind of not take those into account right now because those tend to be small contributors. Your big guys are your wheel force. So how hard are your wheels twisting times, well, is equal to the amount of drag force that your system is feeling. That is easily calculated using this guy over here, which says that your aerodynamic drag is equal to 1/2 rho, which is the density of air, which density of air at sea level is 1.226 kilograms per cubic meter, times the velocity that you're traveling squared, times the frontal area of your vehicle, times the coefficient of drag. Well, what does all that mean? Well, if you look at this guy over here, this is my son's truck again. You see that, you know, I've got, the body, which is right here, which has a certain area that, the wind sees when it's shooting through. Then I also have these big tires over here. So you factor these guys together, this gives you a frontal area that, is the main factor of how much air are you displacing when you're pushing through at high rates of speed. Now, there's an efficiency term in here. So if you look inside this my Rustler here, this isn't just a flat plate pushing through. So it's streamlined. It's got some nice subtle curves and everything. So your coefficient of drag is the relationship between how well or how efficiently air really flows over your vehicle versus a notional flat plate. So going back to the equation, looking here, so this is my dynamic pressure. This tells me, based upon how fast I'm going, what is the available pressure that can push on my object. And over here, this tells me how big my object is and how efficiently air flows around it. Simple relationships, and it's all done. We can thank our good friend Bernoulli for giving us the relationships that garnered this equation, but that's a discussion for some other time. So, again, looking at this nice lovely equation, you can see that as you increase in speed, the amount of aero drag that you feel actually increases with the square of that speed. So what that means is whenever you double your speed, you're actually quadrupling the amount of aero drag that you see. But again, that's not the whole story. So let me go ahead and jump through, and since this is a discussion of speed, or actually force and power, you have to take into account the power side of the equation. Now, I'm going to take a little step backwards and just go to first electrical principles. When you talk about power, what is it? Well, power is really a measurement of the flow of energy. Okay, so for electrical systems, you can calculate the power that they dissipate, and that's really what you're doing. You're dissipating, and I'll get there. But so your power of an electrical system is equal to the current that is pushing in the system times the voltage that is running at. There's also a mechanical equivalent of there, and that is torque is equal power. And in mechanical systems, we usually talk about it in terms of horsepower. But horsepower is equal to torque that your system is feeling times omega, which in this case is the RPM that the wheels are spinning at. But that's also equal to aerodynamic power. And this is one that a lot of you guys probably haven't seen before. But you take that aerodynamic drag term that we calculated earlier, and you multiply it by velocity again. So now you end up with a relationship of aerodynamic power. So this is how much power are you dissipating trying to push your vehicle through the air, and that's equal to 1/2 rho v cubed times your frontal area times your coefficient of drag. So now, if you double your speed, you're actually consuming 8 times as much power in order to do your job. That becomes important a little bit later, because here you see that if you sit down and crunch through the math, for our types of vehicles, so a Rustler, and it doesn't matter in this situation if it's a 6S, if it's a 1410, the mass doesn't matter as well, because all you're really doing is measuring how hard it is for the vehicle to push itself through the air. And from the air's point of view, looking at it at this angle, it doesn't care if this vehicle weighs 1 pound or 100 pounds. It still has the same area, and it's still pushing through at the same rate. So that same amount of air is flowing over. So aerodynamic drag is completely independent of vehicle mass. So jumping back through, so whether I'm driving Draven's 114 mile an hour monster rustler, or I'm driving, a straight out of the box RTR, if I take those same vehicles to the same treatment up to 100 miles an hour, my aerodynamic drag, and actually aerodynamic drag plus mechanical losses and a bunch of other factors that I threw in this ridiculous little spreadsheet here, you know, all this math tells me that at about 100 miles an hour, you have to draw about a kilowatt from your battery pack pushing through your ESC in order for you to maintain that speed. So, looking at the equation up here, if we assume, my 3S LiPo setup, so running at about 11 volts, I have to push approximately 100 amps. And you guys are going to probably catch me on this. It's not exactly 1 kilowatt, but this is just approximations here just to show how the equations work. But 11 volts, you have to push about 100 amps in order to generate 1 kilowatt. But the nice thing about the 6S LiPo guys is that at that situation, you're actually running at twice the voltage. So you can end up getting the same amount of power at running at about 50 amps. What does that do for you? Well, if you look at these guys, your speed controllers and everything, what you're going to find is that one of the big limitations of the system is how much current can these guys handle. And, you pick up a cheapo Hobby Wing or something like that from Hobby Parts, and you're going to see that, these are 30, 60, maybe 100 amp speed controllers. You can get 150 amp versions as well. But when you're pushing amperage, you're literally, amperage is a measurement of how many electrons are being forced through your wires. The higher your amperage, the more internal friction there is in the wires. And yes, there is internal friction in the wires. And when you start to push these monstrous amounts of current, your wires start to heat up a lot. That goes through your motors, and everything starts to consume a lot of power. The motors start to, they heat up tremendously, and you can end up literally melting things. So if you can run at a higher voltage, you can get the same amount of power out of your system with, much smaller wires, much less risk of disintegrating things by all the heat that's generated just by moving around all that current. So don't get me wrong, there are inherent advantages to running at the higher voltages of the 4, 5, 6S LiPo setups. But again, I'm trying to save weight, so I'm taking a little bit different tact. But back to my discussion about speed and drag and power, again, at 100 miles an hour, you're consuming about a kilowatt of energy, or about a kilowatt of power. But if you increase that to the mythical 114 mile an hour level, I've increased the amount of power being consumed by 1.5 times. So that goes to about 1.5 kilowatts. I go just a few mile an hour faster to 120 mile an hour, and all of a sudden it goes to 1.7 kilowatts. So trying to get much above this, you're starting to get into some really truly monstrous amounts of power for such a small vehicle. So, and that's part of the reason why we see a brick wall out there for people trying to get beyond these speeds, because, as again, power dissipation goes with the cube of velocity. And these are really, really large velocities for really small vehicles. So there's another big factor, and that goes into how you actually get that power generated by these vehicles, by these engines. And there's some kind of surprising results in here, because I'm going to get really geeky on you guys, and I apologize, but it's worth it at the end. So let me just show you. So when you look at mechanical power, the textbooks will tell you, and like I mentioned before, that power is equal to torque times RPM. So for an electric motor, a brushless motor, what you find is that the torque that it can generate is equal to the number of poles in the motor times the magnetic flux, and that's physically how big are your magnets, how large is the magnetic field that you're able to generate, times the current that's passing through it. Now we go over to this side, your RPM, as it turns out, is really primarily a function of the voltage. of your system. And we already know that voltage equals kV times, I'm sorry, RPM equals kV times voltage. But here, looking at the explicit math, your voltage that you're applying to your motor times, well, I should say your RPM is really your voltage that you apply to the motor minus this term right here. This is actually a measurement of the internal resistance of the motor, and I'll talk more about that in a second, divided by the number of poles times that magnetic field, again, that we're talking about. So this is a pretty interesting term right here, because this is a measurement of how efficiently your motor can turn electrical energy into power. So that becomes part of your loss, your drag consideration. And I'll tie that together in just a second. But if you take the math and you multiply all this through to just try to get your ultimate electrical power, a lot of these things fall away. So your magnetic flux is on both sides. They actually cancel out. Same thing with your current. So ultimately, for your measurement of power, it all comes back down again to a measure of the current that you're able to supply to the motor times the voltage that's on the motor minus the statement of internal resistance. Now this looks like it's a big number because you have I squared, but remember, well, some of you guys may not know, but in order for these motors to run, they have to have fairly low internal resistances. And those internal resistances are actually they're a property of the length and the quality of wire going through the system. So how many turns are in there, what gauge of wire is being used, so on and so forth. So companies like Castle, who make their business on making super high powerful motors, know that in order for this motor to be able to accommodate 100, 120, or 150 amps consistently, they have to size all the internal components to match what they need for their power application. And also, they need to set the size of these of the magnets inside of there in order to give them the instantaneous torque numbers that they want for that application. So, but all those balances are all part of their secret sauce. These are all trade secrets. They're not going to tell you what these numbers are, but you know, the right people with the right equipment can easily measure it. But like I said, this internal resistance number, that's a physical property of the length of the wire, length and gauge of the wire that's inside the motor. The flux, physically a measure of or a property of the size of the magnets in the motor. But again, the math says it doesn't matter. So I can get the same amount of power out of my 1410 setup here as I can get from a 2200 kV Mamba Monster if I can push enough current. So again, that goes to, you know, part of the big limiting factor of these systems: how big a battery can you get, and how much juice can you physically push to your electronic speed controller. That's one of the reasons why I'm such a big fan of the Castle Creation setups, because they seem to have that all dialed in. So just pulling it all together, if you're trying to make a fast vehicle and you want to understand what's really going on behind the scenes, you know, it's worth it to sit down and take it and do a little research. It doesn't take that much, and figure out how all these things fit together. Now, some of these relationships are more complicated than others, but that's part of the reason why I'm trying to make these videos, in order to help be a guide to help people see how it all fits together. In my line of work, that's called systems engineering, seeing how everything fits together, and how, you know, to be able to take a step back and try to manage, am I spending my money and my resources in the right places for the application that I'm trying to go for, so I don't end up breaking things that I didn't need to buy in the first place. So again, this is Our House 21 signing off. I hope you guys find this useful. Please feel free to comment back and tell me, you know, what I did well and what you didn't like, and other topics that you might want me to address. Because there are actually several other really big topics that can be poked at inside of here. Because things I didn't talk about, such as, you know, when you're pushing this much current, there's voltage drops inside your inside your battery because of internal resistance. That's actually going to drive your 11-volt battery pack down to something like maybe 10, maybe 9.5 volts. So you need to understand some of those internal resistance factors while you're trying to set your gearing, so that you can try to figure out what voltage are you really going to be running at, so that you can set your kV values at the right level, so that you can have your overall RPM where you need it to be in order to accomplish your goals. And there's also a lot of possible discussions about your gearing selection and what that does to your overall acceleration, what that does to the amount of wheel torque that you're able to put down to the ground, and ultimately what that does to the performance of your vehicle. So it's a rich topic. There's all sorts of cool things that we could talk about, and cool ways that you could break your vehicle and fix your vehicle and then break it all over again. Because ultimately, that's part of the fun of this whole thing. This little chassis right here has been torn to shreds. This was the original chassis that came with this guy. But when I destroyed this thing, I didn't mind at all, because it's all part of the mantra: fly, fix, fly. You break it, you analyze it, you fix it, and you do it all over again. And that's all part of the fun. All right, so again, our House 21 signing out. I hope you guys enjoyed. Let me know what you think. Later.